આજે 2 લેક્ચર હોય. લેબ હોય તો 2 વાગે એટલે લાઈટ આવી જઈશ.
Okay, so I shall start the presentation now. Please confirm that you can see the presentation. Hello?
Yes, sir.
Okay, thank you. Please mute your mic. So, this was the topic that we were discussing when we ended the last class, that of Newton's gravitational constant and its implications. So we began the discussion, we left it half complete. So today we should be able to complete that discussion. So just a minute. Yes, can you please confirm that you can hear me clearly and see the presentation?
Yes, sir.
Okay,
Yes, sir.
thank you. Thank you. So, as I said, so the first thing that we appreciated about gravity was that it was a mechanical effect. Mechanical effect meaning that there was a mass and the mass was exerting a force, and under the effect of that force, particles were drawn towards it. This is the basic principle, mechanistic principle of gravity. So escape velocity is the sort of velocity that you can impart on a particle that will overcome the gravity of a central mass and move out of its influence. So what happens when the escape velocity is equal to or the speed of light? Meaning that if you have a certain massive object, then the more the mass and smaller the radius, that was the point we were discussing, as you can see from this formula. Greater the mass, smaller the radius, larger will be the required velocity to escape the gravitational field of that object. Typically, these are very massive objects, and you will find such masses in the astrophysical context, not in the context of smaller objects. So now this ratio m by r naught, m being the mass of the object and r naught being its radius, if it becomes very large, there will come a stage when it will prevent even light to escape the gravitational field. And if light is unable to escape, then any observer standing far away will not be able to receive any light from that object. And so as far as that observer is concerned, this whole package of matter might as well be black. So you call it black object, but where's the idea of the whole? I mean, it's after all a solid object, right? I mean, it's packed in matter very compactly, as we mentioned in the last class, that you have to have a large mass and you have to have a small radius. I've given you a problem sheet to work on where you are to use this formula and find the corresponding radius of the sun. You know the mass of the sun, that's 2 into 10 raised to 30 kgs. G and c squared are universal constants. So to be able to convert the sun to a black hole, what is the radius? The radius will be 3 kilometers. In the case of the Earth, 6 into 10 raised to 24 kg is the mass. And the corresponding radius, remember, to form a black hole, meaning something from which even light cannot escape, you have to fulfill 2 criteria. First, you need to have a large mass. Well, that is there, but that by itself is not enough. You also need to pack in that large mass into a very small radius. Typically, these astrophysical objects are spherical in configuration. There's a good deal of fluid mechanics behind that. Maybe later we can have a discussion on that. when we talk about some fluid systems, fluid problems in physical systems. So you have to compress the entire planet Earth with everything that is there on it into a marble-sized sphere of 9 millimeter radius. So that will convert the Earth to a black hole, but of course that can't be done. Now, I want to make 2 points. I mean, we finished this discussion at the end of the last class. First, you can very well say that, fine, that's all right. I mean, this thing will not allow light to escape. Then you should be calling it a black rock, a black sphere, a hard black sphere which is so compactly pressed in that it wouldn't, its gravity is so strong that light is not able to come out. Why are you using the word hole? That's the next question. That's first point. The second point is that this simple theoretical discussion or mathematical discussion that we have had to find the value of the Schwarzschild radius, this whole treatment, the Schwarzschild radius of a spherical black hole. Planet Earth is a sphere. The sun is a spherical configuration of gas, hot plasma, in fact. So they are all in a spherical configuration. The question is that, I mean, this is the radius of that, R as in radius, capital S as in Schwarzschild, named after Carl Schwarzschild, right? So Schwarzschild black hole. This derivation, this result that you have, Schwarzschild radius is equal to 2gm by c squared, is a correct result. However, this derivation, this little derivation, I'm cautioning you, this little derivation should not be considered too seriously. There are certain I mean, it's let me just put it in simple language. It's not really a very rigorous derivation. We are just using our simple idea of school level gravitational theory, and then we are forcing the escape velocity to be equal to the speed of light on the left hand side, and we get this formula. Fine, that's correct. I mean, the final result is correct as far as the result by itself goes. But this derivation should not be considered to be a very rigorous one. So take it with a pinch of salt. However, for the sake of simplicity, I've gone ahead with it because at the end, ultimately, I mean, you're getting the correct result. That is one thing. So that's one thing. Now we shall have to look at this whole idea of the word hole. You could have just called it a black rock or something, you know, or whatever. But why are you calling it a hole? It's after all a solid object. A hole implies empty space, right? Something through which you can burrow or dig through or whatever. So that is the thing that that is the idea that we shall take up now. And why are we going to take it up now? Because I told you we are discussing the implications of the fundamental constants C, H, and G. We finished the discussion of C and H in the last class. Now we are taking up G. What is the importance of G? Let us see. Gravity as geometry. I told you at the outset today that here, whatever we have discussed, we have looked at gravity, Newton's gravity, from the point of view of mechanics. Mechanics, as in that there is a certain amount of matter present, mass is present, and that is then that's causing a force. All these things are mechanical things, not geometry. I mean, in school, you would have studied geometry as a separate subject from the mechanics that you would have studied in physics. Now let us see what is the implication of it. Here, I have drawn, I've written something here in the top left panel, gravity, 2 arrows. One is field, and below that is Newton, and the other is geometry. Below that is Einstein. So we have to understand the implication of this whole connection. So geometry, I mean, basic geometry, here's a coordinate grid. You have a 2-dimensional geometry. You have the x-axis, you have the y-axis. I've written something over here, geometry of space-time in gravity-free condition. Let us first just try to understand geometry in itself. Geometry is something that exists only in your mind. It's a mental construct. Like right now, you are sitting in your room, I expect, and so your room is very, very likely cubical or cuboidal in shape. So if you look at your room, you can identify a, a vertex on the ground in some corner, and one edge of the wall, a wall and the floor, between the wall and the floor, you can term it as the x-axis, another edge perpendicular to it along the same floor, you can term it as the y-axis, and then perpendicular to both these x and y axes, you have the z-axis going upwards towards the ceiling. So all of these start at the vertex. Now, at least the edges that you can see in the corner of your room are visibly there for you. But in reality, I mean, when you look out, for instance, you say that the sun is at the origin of coordinates. Let us imagine the sun to be at the origin of coordinates. The sun is at the center of the solar system, and the planets are all going around it. So all this whole business of center of the solar system, origin of coordinates, and the planets going around all around, these are things X, Y, Z. Nobody has painted an x-axis or a y-axis or a z-axis in space. You are just conjuring them up in your mind. So you would have thought that geometry is more like a mental construct which you fit onto the world, and then you try to mathematically quantify various phenomena in that world with this geometrical tool, some sort of a grid. So here we have some sort of a two-dimensional grid. You can extend it to 3 dimensions, of course. And don't forget something. We have already discussed this point. Einstein showed that the universe that we actually live in is, in the most general sense, a 4-dimensional universe defined by a set of 4-dimensional coordinates, x, y, z, and ICT, right? So when you say x-axis, when you say y-axis, you have some idea of a length in your mind. By the way, you can see very well that a 4-dimensional coordinate system is something which you can't even imagine, right? These are all mathematical constructs. And I told you once earlier that mathematics is really an extension of philosophical exercising. In the sense that there is no such thing in reality as infinity. I told you this earlier. And if infinity doesn't exist, because after all, the universe is a finite object, a finite system. So how can something that is finite accommodate infinity? So if the universe is finite, then it can't accommodate infinity. But infinity is there in the mathematician's mind. And then the inverse of infinity is 1 upon infinity is 0. Therefore, the zero idea, I mean, 0 really ought not to exist in nature. So there has to be a minimum non-zero quantum, probably. And we have tried to see what that minimum non-zero quantum can be. We called it minimum non-zero quantum in space, that is, and we called it the Planck length. And similarly, likewise, we have a minimum non-zero quantum in time. You can very well see now that if there's a non-zero quantum in space, there ought to be a non-zero quantum, minimum non-zero irreducible quantum in time as well. You will ask me why? Because I say that thanks to Einstein now, space and time are both placed in the same category. So there is not much difference between space and time if you went by this formula, if you were to go by this formula. So if space is quantized, time ought to be quantized as well. By that simple statement, I mean, there's no rigorous mathematical proof behind it. I'm saying that the status of space and time are the same. Now, you can still, you can go up to X, Y, and Z axes, and you can say that, okay, when we say x-axis, we define a unit vector on x-axis. This is 1 meter. You can imagine what 1 meter length can be. Incidentally, you can't even imagine what time can be like. Do you have an impression of time on your mind? No. You can imagine space, right? Time is in the 4th dimension. So the universe is like that in 4 dimensions, right? Now, let us try to see. For simplicity, I have just drawn a two-dimensional universe having two axes, x and y. Well, ideally it should be x and t because I mean space and time, but I've just drawn x and y. Okay, that's all right. That's not the big issue over here. Um, I've written something over here, geometry of space-time in gravity-free condition. Here comes Einstein's idea of gravity. You follow extremely carefully. I told you just now that space is something that you imagine in your mind. Coordinates, x, y, z, these are mathematical constructs. Nobody has drawn a radial vector in the solar system, or nobody has drawn x, y, z axes in space for you to understand. You would think that they were just there, just tools, convenient tools for you to quantify natural phenomena. Now comes Einstein, and he says that space and time are real physical entities. What do you mean by real physical entities? What is time? You would think you really don't know what time is. You can't put a word to it. What is time? You just say that between two events, for instance, the movement of the hand on your watch, or a particular second hand or minute hand or hour hand on your watch, and those are marking events, and whatever elapses, something elapses between two successive events, and you call that the passage of time. Maybe you measure it as 1 second, maybe you measure it as 1 minute, 1 hour, whatever. So it is there. Now comes this radically different idea. Try and imagine this is like a bed sheet. You know, a bed sheet, a rectangular large piece of cloth. Imagine that this bed sheet, four of you are holding four corners of the bed sheet. Follow this point extremely carefully. Four corners of the bed sheet, four of you are holding, and you are pulling it out straight and tight and taut, and the bed sheet will be like this. Right. Now then I come along and I put a large object, let's say a heavy object, a small and a heavy object, let's say a cricket ball, which is small and it's a heavy object also. So it's denser, it has got more density, packs in more matter in a certain radius than, let's say, a football. A football is larger, but it's that largeness is spread out with a smaller amount of mass. Whatever it is, a football is less dense than a cricket ball. Proof: a cricket ball will, well, I mean, you can find the density of it. Although I think both a football and a cricket ball will float on water, because the cricket ball is made of cork inside, so that's lighter than the football material. Anyway, so what happens is that four of you are holding this sheet in four corners, and I place a cricket ball over there, or maybe a paperweight or whatever, something that's heavy and small but heavy. So what will happen immediately? It will cause a bit of a sagging in the tightly spread out sheet. So if your sheet, let's say your sheet was a white sheet on which you have drawn coordinate axes, like, these, like as you would do on a graph paper. So you could immediately see that as soon as the ball is, or this whatever sphere or heavy object is put in the sheet, it'll distort the structure of the sheet, because under the weight of the object, the sheet will sag down a little, and the coordinate axes that you would have drawn on the sheet would be distorted like this. Okay? That is the idea of Einstein. What is gravity? Newton's gravity is field. What do I mean by field? Only in the last semester you studied electromagnetic theory. A positively charged particle will throw out radially outward diverging field lines, and negatively charged particles will draw in radially converging field lines. So you place another charge in that field. The second charge, the test charge that is, does not directly interact with the charge that has caused the field, which is known as the source charge. I hope you are recalling all this jargon: test charge and source charge, all these things, right? The test charge and the source charge, they do not experience any direct interaction. The test charge interacts with the field created by the source charge. And therein, the interaction is a force. And so you have a mechanical interaction. So Newton's idea of gravity was like that. You have a massive object and it creates a gravitational field all around. Let's say the sun and the earth. The earth and the sun are not touching each other, right? And yet the sun's gravity is pulling the earth towards it. How is it happening? It's not like a very visible direct interaction, like the way you would hit a cricket ball with a bat, and the cricket ball will feel the force of the bat through a direct interaction. In the case of the sun and the earth, it's an indirect interaction. But how is this indirect interaction taking place? The direct interaction is taking place through the mediation of the field. The earth is not acting directly with the sun, but the earth is acting with the field produced by the sun. That is a direct interaction. But without the sun, the field wouldn't be there. So anyway, that was Newton's idea of gravity. Now Einstein's idea of gravity. Space and time. You follow this point now with full attention. Space and time are not geometrical or mathematical abstractions as you would think. They are physical realities. Very important point. They are physical realities. Just like, let's say, I throw a ball or a cricket ball or any such thing, very hard object at a glass pane. It will break the glass pane. Or I throw a very object or a very heavy object at, let's say, some metal surface. It will cause a dent in the metal surface. The metal will not break as glass would. It will cause a dent in the metal surface. Why is this sort of a thing is happening? Because the metal surface is a physically present object and it feels the direct interaction with other physical objects, right? So it was that Einstein's view was like this, that space and time are real physical entities. They are not mathematical abstractions. So when you place a very massive object in space, it will distort the geometrical structure of space. You would have thought that the geometrical structure of space was just a mathematical abstraction, just for mental, it's there in your mind only for the sake of convenience of providing a mathematical description. No. So if there were no massive object in this space, let us see, you have x, y. If there were no massive object in this space, two-dimensional that we have, so the geometry of space-time will be flat like this, straight parallel lines like this. However, if it were to have the presence of matter, presence of mass, then the geometry would be distorted, warping of geometry due to gravity. Now don't forget, Einstein also argued that space and time were physical entities and they are in a four-dimensional grid. Just like what can happen in a two-dimensional grid, the same thing can happen in a three-dimensional space, and the same thing can happen in four-dimensional space as well. That is the important thing. Although I've drawn a very simple diagram, just 2Ds, right? So now, let's see. The geometry of space-time is physically influenced by the presence of matter. So this is the whole idea of gravity. Light follows paths known as geodesics in the geometric grid. Let us now try to understand what I mean. If you are in the presence of a massive object, you'd fall towards that massive object. That is gravity. That is Newton's gravity. Einstein's gravity, you'd fall towards that massive object because the massive object will exert a force on it. What is the force? Minus g capital M small m by r squared. That is the force exerted by that object. And under the influence of that force, you'd be. So that is Newton's mechanical point of view, mechanical. Einstein's geometrical point of view says that you'd be falling towards that object because the space along which you are able to travel will be distorted towards that object. So that is why, so suppose there was no massive object over here, and here you stand, and you will move straight along this path. But now suddenly you have a massive object over here. So the path would have bent, and you'll be going drawn towards that object if you were to move along this path. That is the whole idea of Einstein's gravity. That space-time are warped and things keep moving towards a gravitational, a massive object because the space-time path that it has. Note my use of the word space-time. We are talking about a four-dimensional grid, x, y, z, and t, both three coordinates in space and one coordinate in time. So that is what happens. Now, what about light? Light follows paths known as geodesics in the geometric grid. Let's try to understand what is a geodesic. Between any 2 points in space, let's say I just ask you what is the shortest path between 2 points. You imagine 2 points on your tabletop, flat tabletop, right? What is the shortest path between your between 2 points on your flat tabletop? It is a straight line. But is that true when you consider a surface like the surface of the Earth? The surface of the Earth is not a flat top. It is a spherical surface, almost a spherical surface. So suppose you have to go to the North Pole from where you are. Let's say you are sitting in India right now. So you have to go to the North Pole. The straightest path, straight line distance between the North Pole, if you have to travel by, then you have to dig through the Earth. That is not what you do. You have to travel along the surface of the Earth. And that surface, that path is not a straight line. The shortest distance between any 2 points on a spherical surface is not a straight line, is not on a straight line. The shortest distance between any 2 points on a spherical surface lies on what is known as a great circle. I believe that in school geography, you would have studied of this thing, great circles. Lines of longitudes are great circles, not the lines of latitude. The only latitude that is a great circle is the equator. What is the definition of a great circle? It is an imaginary circle that you can draw on the surface of a sphere whose center, the center of the circle and the center of the sphere will coincide. So the only latitude whose circle of latitude whose center coincides with that of the Earth is the equator. But all longitudes have their centers at the center of the Earth. Therefore, all longitudes are great circles. So light follows in this four-dimensional space-time grid. Light follows a similar kind of a path, right? So known as a geodesic. So lines of longitudes are geodesics. And so near massive compact objects, light path is bent and deviated. Let us now see this, connect this idea, this point C will connect, we will connect this idea to the word hole over here, because we are now trying to understand the use of the word black hole. We are not calling it a black rock. We are not calling it a black sphere, right? We are calling it a black hole. Why are we calling it a black hole? Here's the idea. 4 of you are holding this cloth sheet tightly in 4 corners. I put a paperweight. I put a cricket ball. And more and more massive and compact an object that I put, greater and greater will be the warping or the distortion of the geometry of space-time. Now what happens, I put an extremely heavy object, let's say a lead ball. Lead is the heaviest of all elements, non-radioactive elements. That is, by the way, when you do your lab and all these things, physical systems, lead will figure in a very serious way because we'll be working on a good deal of radioactive problems. And so lead ball, let us say, it's a very heavy object. What will it do? It will do this. Tear a hole in the cloth, because the cloth will not have enough strength, material strength to sustain such a heavy weight, and the lead sphere will just tear the cloth and fall through. And what will be left behind is a rupture. Similarly, just see, without any massive object, you had this nice, neat, ordered coordinate grid. You place a massive object, the coordinate grid gets distorted. When you have an extremely massive object, what is that massive object? This thing. An object which has got a large mass and a radius that is less than or equal to the radius, the Schwarzschild radius. You have that, that thing is so compact, so dense and massive, that it will tear through the fabric of space-time. So a black hole is a rupture in the geometric fabric of space-time. And what is the behavior of light? So if no mass were to have been present, light would have traveled along these straight lines, these arrows. With the presence of mass, the light path would be a bit deviated. Near massive compact objects, the light path is bent and deviated. Now, but light needs a continuous passage along a geodesic. But suddenly, let's say along this path, light is traveling and suddenly it comes over here and finds that there is no continuous path. There is an absence of space-time. Carefully note that point. I've used the word absence of space-time. I did not say vacuum. Vacuum is space with no matter, but space still exists. But here, there is no space or time. This is the edge of the hole, the pit. You know what a pit is? A pit is a bottomless hole, really, a deep abyss, something like that. So light will come here and fall into this and will not be able to come out. So this dotted circle is known as the event horizon. You will not be able to see what is there beyond this dotted circle. Therefore, you call it the horizon. What is a horizon? A horizon is something far out in the distance beyond which you will not be able to know what is going on. I mean, on the other side of the horizon. So a black hole, so that's the whole idea. I mean, that's the idea of having a hole in this thing. A black hole is a rupture in the geometric fabric of space-time. Light does not have a continuous passage through this rupture. So, but you will immediately say that, okay, that is fine. But will space suddenly develop these little ruptures or tears in them? Well, the answer is not quite, not really. You would still need some presence of matter, very massive presence of matter, packed in a very small radius to create this whole rupture in space-time. After that, once it has been created, then it becomes a hole. The black, this thing, this whole discussion that I held in the previous page, this is just a black rock. The word hole now refers to the absence of space-time. There is no space, there is no time here. So you just fall through straight away. So basically, this is a geometric idea of a black hole, or this is a geometric idea of gravity, but you still need the presence of matter, presence of mass to create gravity. So as soon as you talk about the presence of mass, you are bringing in mechanics, right? The physical element of mechanics is matter. Just like the physical element of electromagnetism is a charge. Charge static or moving, electricity is always there. Charge moving, only then you'll have magnetism. So it is that for mechanics, you need the presence of matter. So we were discussing the role of the fundamental constants. I told you that they are like bridges. I mentioned to you that here you have this thing, here. Space and time were seen to be two different mechanical dimensions. The speed of light brings about a unification, builds a bridge between space and time. So speed of light is a unifying fundamental constant. It also unifies energy and mass. Planck's constant unifies wave and particle natures of matter. And Newton's constant of universal gravitation, capital G, what does it unify? It unifies a mechanical view of gravity due to Newton with a geometric view of gravity due to Einstein. And that point has been written over here. The gravitational constant G connects Einstein's geometric view of gravity with Newton's field view of gravity, mechanical field view of gravity. That is important, right? So that is the third fundamental constant I wanted to talk about. Now let us go to another fundamental constant, although it it's something that doesn't occur for small for a single particle, it's not relevant. For a single particle, C is relevant if that particle is traveling close to the speed of light. For a single particle, G is of course relevant if it has mass. For a single particle, H, Planck's constant, is relevant because apart from being a particle, it is also a wave. So single particle has got mass, therefore it will exert gravity, therefore G is relevant. A single particle has got a wave-like attribute, therefore H is relevant because H bridges the wave-like character of matter with its particle-like character. If a single particle travels close to the speed of light, C will be relevant to bring in all the whole host of theories Einstein put forward. Now we are looking at not a single particle, but a large aggregate system. How large? Very large, something of the order of Avogadro's number. What is Avogadro's number? 6 into 10 raised to 23 molecules or particles per mole. What is a mole? There are two different ways of looking at a mole. The chemist's way of looking at a mole is molecular weight expressed in gram. This is something that we learn at school already. I give you oxygen gas, O2, the oxygen gas, molecular oxygen, that is O2. What is the mass of oxygen atom? 16, right? Note that I'm not using any unit. I'm just saying 16. What is the mass of molecular oxygen, O2? 32. Similarly, what is the mass of atomic nitrogen? 14. Mass of atomic molecular nitrogen, N2, is 28. 16 watt, 28 watt, 32 watt. I'm not saying that watt. If you write 32 grams of molecular oxygen, then the number of particles contained in those 32 grams of molecular oxygen will be equal to 6 into 10 raised to 23. If you consider 28 grams of molecular nitrogen, N2, 28 grams, number of particles contained in those 28 grams will be, molecular nitrogen will be 6 into 10 raised to 23. So for any element, molecular weight expressed in grams will give you Avogadro's number of particles in that amount of matter. That's one way of looking at it. Mole is molecular weight or atomic weight expressed in grams. A physics way of looking at one mole is number of particles equal to Avogadro's number defines one mole. If you have an amount of matter containing 6 into 10 raised to 23 particles, then you say that this is 1 mole of substance, right? Let us now try to understand that. A mole is Avogadro's number is a very large number. How large is it? 6 into 10 raised to 23. Let's see. Molecular hydrogen, H2. 2 grams. 2 grams of hydrogen. 2 grams is something that you will barely feel. Or atomic hydrogen, H, right? 1 gram will contain 6 into 10 raised to 23 particles. You are barely able to look at this number. I said in
Sir,
MLT. Yes, hello?
sir, but how scientists found the number of elements, number of atoms in 1 gram of hydrogen? How they
Who,
found out that?
or how do you find that out? You can actually find it out by a very simple way. Uh, you can find it out. Never mind scientists. If I tell you what is the mass of a proton, and atomic hydrogen is proton only, right? So if I tell you the mass of a proton,
Yes,
which is 1.67 into 10 raised to minus
yes, yes.
27 kg,
I got
so
it, sir.
yeah, you'll be able to find it out. But no, it's not nothing as simple as that. The first people who investigated it, they had to do it in a pretty roundabout manner. But anyway, I'm not getting into that discussion. So, yeah, so sorry, just a minute. 1 gram of hydrogen is a very small amount. You'd barely be able to feel its touch on your fingertips, right? It's so small. and yet it contains 6 into 10, 6.023 into 10 raised to 23 number of particles. How large is that number? Just think of it. Here I have written something. What is the age of the universe? The age of the universe is 10 raised to 17 seconds. So just a small amount of matter, 1 mole of hydrogen 2, H2, 2 grams is 1 mole, containing 6.023 into 10 raised to 23 particles per mole. So that amount of matter has got 10 raised to 6 into 10 raised to 23 particles. So 23 minus 17 will be 6. So 6 million times more than this number of 10 raised to 17 seconds. So suppose you were some kind of an untiring machine counting every particle per second, right? Every second you lift a particle, and every second is a normal time scale of our activity. You lift a particle from a little box that contains H2, 1 mole of H2 molecules. You lift a particle and put it in another box. To count the number of particles that are there in 2 grams of H2, you will need 6 million times longer, 6 million times longer than the present age of the universe. That is the largeness of Avogadro's number. Why is large aggregate important? Because we may be talking about single particle here, there, a single particle moves at the speed of light, a single particle is moving, and so it has got a wave-like character. A single particle is exerting gravity. You can approximate the sun as a single particle. You can approximate the earth as a single particle. Are they really single particles? They are large aggregates of particles. That's the reality of nature. Therefore, you shall have to look at nature when it comes in large aggregates. Let us see how. Here you have the ideal gas equation. Simple argument. You are familiar with the ideal gas equation. P into V is equal to small n RT. Pressure, volume. Small n is the number of moles. What is the number of moles? 1 mole contains Avogadro's number of particles, right? And total number of particles divided by Avogadro's number of particles will give you the number of moles. So if I have 4 grams of molecular hydrogen, so 4 grams will contain 4 grams divided by 1 mole contains 2 grams of molecular hydrogen. 1 mole is made up of 2 grams. So the 4 by 2 will give you 2 moles of molecular hydrogen. Anyway, so that is what it is. R here is the universal gas constant, and capital T is the temperature. Now you follow the argument carefully, because you remember in the lab last time on Monday, I gave you a problem sheet. At the end of the problem sheet, there were 2 questions on this involving temperature, which I did not discuss because I had not covered that portion in the class. So we will now do that. Let us see. Pressure into volume. Let us just slowly analyze that. Is force per area. Pressure is force per area and volume is volume. So force per area into volume will be, area and volume will cancel and you'll get force into displacement. And what is force into displacement? Work, which is a form of energy. So what is this PV thing? Force into displacement is work, but now instead of force into displacement, you're talking about pressure into volume. What is this thing? It's also work. Pressure into volume is actually a work. But what work are you doing? See, if you think of a gas tends to fill all space that is available to it. Unless you put container walls, gas will spread in all directions as far as it can go. That much is not very difficult to understand. So if you want to contain gas within a finite or bound region of space, you will have to build container walls, or you'll have to force the gas to remain confined there within the container wall. So basically, this whole business of confining a gas requires some work. Suppose a car is trying to travel slowly, let's say. You are a very strong person and you're forcing the car to stop. So if you're a very strong man, like, all these shows where you have powerfully built bodybuilders, they try to stop, moving vehicles or something like that. So you will put your hands against the car and force it to stop. Otherwise, the car would rather be going forward. So it is a gas would rather be spreading outwards in all directions, and you are forcing the gas to stop by building container walls all around it. Nevertheless, the gas will continue to exert force against the container wall, and that force is understood to be pressure. Force by area is understood to be pressure. So basically, P into V is the work done on the gas to confine it. Okay. Now, PV is equal to nRT. So basically, if you do all the work, if you do work to confine it, work is a form of energy. It is going into the gas, right? And just like if you force a car to stop, the car has got its own kinetic energy with which it would rather be moving forward, but you are working against the car. So your work is going into the car to negate its forward motion, like that. And so it is that the work that you are doing to confine the gas is going into the gas as its energy. So it is basically the energy contained in the gas, roughly speaking, order of magnitude. So now you just see small n, number of moles. You follow this discussion carefully now, is equal to capital N, total number of particles, divided by Avogadro's number, right? So PV is equal to small n RT. Small n I've written as capital N by capital NA. N subscript A is Avogadro's number. N as in number, capital A as in Avogadro. Then I'm taking the capital N to the left-hand side, and I've got PV by N. What is PV? I said that PV is the energy contained. So energy contained by capital N. That will be the average energy per particle. Energy contained per particle in an average sense in the gas, and that is of the order of magnitude. I'm not writing an exactly equal to formula here, of the order of Boltzmann's constant into T. What is Boltzmann's constant? In measurable terms, it is the universal gas constant divided by Avogadro's number. But it's not just like you already had two known constants. You combine them and give your own name to it and say that this is a new constant. I am Boltzmann and I'm naming this constant. No, it's nothing as simple as that. It's something more fundamental than that. The fundamental thing is that, let us now try to understand. I told you that the nature of fundamental constants is that they build bridges. Speed of light built a bridge between space and time. Space and time were unified in the same category as the speed of light. Planck's constant is a bridge between wave character of matter and particle character of matter. Newton's universal gravitational constant is a bridge between Newton's mechanical field view of gravity and Einstein's geometric view of gravity. And so it is that you have Boltzmann's constant. What have you got? Left-hand side is an average energy. It is a microscopic measure. And the right-hand side is temperature. It is a macroscopic measure. Look at this formula. We will discuss this formula in some detail now. Follow the discussion carefully, all of you. When is averaging good? Averaging is good when the sample size is large. I'll give you a simple example. Suppose in a country there were only two citizens. One is Mr. Mukesh Ambani, who, by the way, is the son of the person after whom your university is named. He is the richest man in Asia. Maybe not right now. Gautam Adani is probably the richest. I don't know. Anyway, he's a very rich man. And the other person is a beggar on the footpath, sitting on the footpath. Suppose you have a situation where you just have these two persons defining a sample, a statistical sample. I will say, well, you find their average wealth. Okay, very good. So what is the averaging technique? You take the total wealth of both persons. In the beggar's case, it is about 0. And in Mr. Mukesh Ambani's case, it is somewhere around, I don't know, $50 billion or something like that, 50 or $60 billion, whatever. 60, let us say, or whatever. 50. So you take the total wealth of these two persons and you divide by 2. Fine. So then you will make the statement that the beggar has an average wealth of something like 25 to 30 billion dollars. You have done nothing wrong. Averaging is just the way you did it. Arithmetically, you have done everything as it should be. You have taken the total and you have divided it by the total sample size. And you found the average number. Arithmetically, everything is perfect. But does it make any sense for you to say that a beggar living on the footpath is, in an average sense, owner of $30 billion? Means nothing. Where have you gone wrong? You have not gone wrong arithmetically. You have gone wrong statistically. Statistically, now you follow carefully, statistically, averaging becomes a good measure when the sample size is large. For instance, just think of this. If you were a class of only 5 students, then if I were to evaluate you in an examination, a class of 2 or 3 students, no, very small number, let's say less than 10, 4, 3, 4, 5, something of that order, then I would not be doing the right thing. I'm not saying correct thing. Mathematically, I'd be doing the correct thing if I do the average. Yeah, averaging principle is fine. You just find what is the total score obtained by everybody and divided it by the total number of students, 4, 5, whatever, get an average number. Everything is fine. But statistically, it would not be a right thing. On the other hand, if you have a class size that is close to 400, your class size is, I think, 360 or 370, something like that, just in the last semester. Mukesh, sir, and I did your grading. What did we do? We took an average first, and then we saw how many students were above average and how many students were below average. And then accordingly, we did the grading win size. But if the class size is very small, then statistically it wouldn't be proper for us to say that this fellow is above average, this fellow is below average. So averaging becomes a faithful measure, a proper measure, only when the sample size is large, right? Now, I would use the word microscopic over here. What do I mean by microscopic? Microscopic means that you go into the system and see the system particle by particle. I mean, basically, the whole idea of averaging means that I'll say, hey, you just find the energy possessed by all the particles. What will you do? You will find, okay, particle 1, this much energy. Now, particle 2, this much energy. And so you, in your notebook, you keep adding, of course. As I said, in principle, this is the thing that you will have to do, right? Except that the devil is in the detail. You have to do this thing. You will have to do this thing for an Avogadro number of particles, meaning that it will take longer than even the age of the universe as it stands now. So, but the whole principle is that averaging is a microscopic measure. But if I were to now look at this formula and I say, you tell me what is the average energy possessed by these particles. Will you go into the system and charge after keep running? Particles are moving fast, by the way, gas particles. Will you be running after each and every single particle and then find what their energy, the energy of each one of a particle is, and then you divide the energy by the total number of particles, all those things? No, nobody finds the average energy like that. There's a much simpler way of doing it. All you have to do is stick a thermometer in this gas system, find its temperature, and multiply the temperature by Boltzmann's constant, find the energy, average energy, like that. Follow this point carefully. Exact individual energy of a particle can't be found from by measuring the temperature of the system. But when you have a large number of particles, aggregate Avogadro's number of particles, there's no point being interested in an individual particle. Since it's such a large aggregate, you just need to look at the whole system as a whole, the system as a large macroscopic whole. And then whole meaning WHOLE, not as HOLE as in a black hole. And then all you have to do is to find the temperature. It's like, the difference between, mm, suppose you're not feeling very well. You have got, God forbid, you've got, let's say, COVID virus. So how will I know that you've got COVID virus if I were a doctor? Will I go inside your lungs and check whether there's virus or not? There's no need to make such a fuss. All I will see is that whether you've got a body temperature or not. In finding the body temperature, I'm just taking a macroscopic view of your health. That is what a medicine doctor does in his or her treatment of a patient. But a surgeon who uses knife and scalpel and all that, a surgeon's approach to a medical problem is a microscopic approach, meaning that you cut open the body, go inside, see things this way or that way. That's the thing. So averaging is a microscopic approach like that. It's an invasive approach, meaning that in principle, you are going inside the system, counting the total energy, dividing it by the total number of particles. But then the same thing can be done macroscopically. And so Boltzmann's constant, Kb, has got a fundamental role to play here. Like I said, all fundamental constants build bridges between different domains of physics. So here is a new fundamental constant that is building a bridge between two domains of physics. One is the microscopic domain, between not, or rather not two domains, two perspectives of physics. One is a microscopic perspective, and the other is a macroscopic perspective. Just a while ago, I mentioned the word pressure. Pressure is also a macroscopic perspective. What is pressure after all? All these particles are moving around very rapidly inside the gas cylinder, and occasionally they are striking the wall of the cylinder. And the little strike will impart a force. So over a unit area of the wall of the cylinder, a certain force will be imposed in unit time or whatever. And so you are not interested in how much force an individual particle is raining on the container wall. You'd rather be interested in the average effect, and that average effect is pressure. So this gross macro effect, I'm sorry, the macro effect, and this macro effect is pressure. So pressure, temperature, these are all macroscopic measures. Corresponding to temperature, the microscopic quantity is energy. Corresponding to pressure, the microscopic quantity is force. You understand? So this averaging will only be good when the sample size is large. Don't do it with 2 particles. Don't do it with 3 particles. Very well it will be if you do it with Avogadro number of particles. So be it understood that averaging is always a very good measure. Incidentally, statistics tells you, some of you keep asking this question, sir, will there be absolute grading or relative grading? What do you mean by relative grading? Relative grading is when you do it with respect to others in the class. Follow this point carefully so that you don't ask silly questions to any teacher again. Relative grading meaning, how have I performed with respect to the others? If I have to make performance with respect to the others a yardstick, then I'll have to find an average. That will tell me what is the background performance of the class. For instance, if I say 2 successive batches I'm teaching, I'll say that this batch is better than that batch. How will I know? For the same kind of examination or anything, one particular batch would have got a higher average score, and another particular batch would have got a lower average score. Then I'll say that, oh no, the batch that's got a higher average score is a better batch. So macroscopically, I'm comparing the two of them. Now, if I say relative grading, so relative grading will be with respect to the overall class performance. And how will I know what is the overall class performance? I have to first find out the average. When is an average a good measure? When the class size is large. So if you have a class size of, let's say, 5 or 6 students, don't worry about what is relative grading or average grading. Relative grading wouldn't make much sense because averaging wouldn't make much sense if the sample size is low. You understand? Make a note of this particular point. I think there is something in statistics called the central limit theorem. Just check. I don't read statistics of late. There it says that if a sample size is more than 30, Then all these statistical instrumentating, finding averages and all those things, they are reliable. But if it's less than that, then better you apply your own judgment. Like, if I were to have a class containing 5 students, Isaac, a very hypothetical scenario. Isaac Newton, Albert Einstein, James Maxwell, Max Planck, Werner Heisenberg. I mean, people like that. They were my students. That's not going to happen. And I make them sit in an examination, and some of them will be doing better, some of them will not be doing as well. That's in the nature of examination. Would it make much sense for me to say that, oh, well, Einstein is the poorest student in the class. Let's fail him by an average or relative grading. That will not. Incidentally, Einstein was a very mediocre student. I mean, his grades at the university were not very good, but that's a different matter altogether. So you can see averaging, relative grading, all these things are operational properly when the sample size is large. Uh, so when you have a large aggregate system, no one individual is any more important than any other. The overall macroscopic view becomes more important. And when we talk about a physical system, the macroscopic view is bridged to the microscopic view through the Boltzmann constant. That is the importance of it. This is a fundamental constant. Microscopic on the left-hand side, macroscopic on the right-hand side. If this bridge were not there, then you would not have been able to connect the two. So it is something far more fundamental. K subscript B, K as in constant in German, because Boltzmann was from Austria. And so in German, the C is substituted with K in most cases, and capital B is as in Boltzmann. So it's some much more profound than simply putting one known constant over another and saying that, this combination of these two constants, I'm putting my name against it. No, something far more fundamental than that. So Boltzmann's constant connects the microscopic view of nature with the macroscopic view. Let us look at another concept of this thing, entropy. Let us see. Here is a formula. This formula was famously given by Boltzmann. S is equal to Kb, Boltzmann's constant, log of omega, not log times, log of omega. Omega is multiplicity, S is entropy. What is the meaning of all this? Let's see. This incidentally is engraved on Boltzmann's tombstone where he is buried. I'll just give you a simple example of what entropy is like. Suppose you're doing a very basic, commonly understood experiment. You have 2 coins and you're tossing them up and down, right? So, what are the possible outcomes of 2 coin toss? You follow this point again attentively. It's a very simple example, but it will help you understand the principle of this formula. I'm not getting into the derivation of all that. What are the possible outcomes? You have coin A and coin B. Both coin A and coin B show head. Then coin A shows head, coin B shows tail. Coin A shows tail, coin B shows head. Both coin A and coin B show tail. These are the only 4 possible outcomes. So in binary terms, we would be able to write 0, 0, 0, 1, 1, 0, 1, 1, like that. Now I have written something here in the box. We are looking at a situation rather than looking at, 2 coins are very easy to understand. Now let us do it with 100 coins, right? Coin A, B, C. Well, you don't use the notation A, B, C any longer because that will only take you to 26. Beyond that, you'll run out of ideas. So you call coin 1, 2, 3 like that to coin 100, right? You toss 100 coins. All 100 coins show head. All 100 coins show tail. So it is that showing all heads or showing all tails are highly ordered structures. 2 heads and 2 tails are highly ordered but have low probability. Similarly, if you were to do it for 100 coins, 100 coins with all heads is an event outcome with extremely low probability. It's not impossible, it's highly improbable. Similarly, all 100 tails is again an outcome of low probability. You can just see what is the probability of getting two heads. What are the this chart has set down four possible outcomes: head, 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 tail, tail, head, tail, tail. Right. Um so four outcomes, four possible outcomes. What is the probability of having both heads? 1 by 4. Head and tail, 1 by 4. Tail and head, 1 by 4. Tail and tail, 1 by 4. So having both heads and having both tails will have a probability of 1 by 4. Now, coin 1 has got a head, coin 2 has got a tail, coin 1 has got a tail, coin 2 has got a head. Where you have got just two coins, it is easier for you to identify, okay, this is my first coin, this is my second coin. Suppose I give you 100 coins, then do you really care which coin is showing head or which coin is showing a tail? Larger the system, ah, stronger will be your tendency to look at the system from a macroscopic perspective rather than a microscopic perspective. So you would rather be considering not which coin has got a head or which coin has got a tail or which coin has got a tail and which coin has got a head, not microscopic. That microscopic distinction will not be very important to you. You'd rather be interested in just a head tail combination. How many head tail combinations can I get? See, this is a permutation. Permutation is arrangement. First coin head, second coin tail. First coin tail, second coin head. These are individual permutations, but a combination. I said, no, let's not worry about what individual coins are getting. Just tell me what is the macroscopic combination. What is the head tail combination? What is the probability of a macroscopic head tail combination? You will say that the probability of a macroscopic head-tail combination is 2 out of 4. This is also a head-tail, this is also a head-tail combination. And there are two ways of getting that. So 2 out of 4. So one head and one tail have a higher probability than all heads and all tails. Similarly, when you do it with 100 coin tosses, all heads and all tails are extremely low probable outcomes, but nearly 50 head and 50 tails will be the most probable outcome. However, now you have something else. Having all heads and having all tails are highly ordered systems. Everybody is very disciplined, all the coins. They fall and everybody shows head. So, well, all the coins are showing tail. So they are highly ordered uh, outcomes, but they are low probable outcome, low probability outcomes. Whereas um, confused clamor of heads and tails is a disordered outcome. Macroscopically, it's a very disordered outcome, but they have a higher probability. Moral of the story, ordering is a low probability phenomenon. Nature's own tendency is to go towards disorder. And entropy, as it comes out of the second law of thermodynamics, uh, is a measure of that disorder. What do I mean by measure of the disorder? Let us see now. A head-tail combination has higher disorder and therefore higher multiplicity. This is the word. Make a note of that word, multiplicity. There are two ways in which a head-tail combination can happen. So that combination has got a multiplicity of 2. A head-head combination has got a multiplicity of 1. A tail-tail combination has got a multiplicity of 1. So head tail has got a higher multiplicity, but head tail is a disordered state. Therefore, the disordered states have higher multiplicity and therefore greater probability of occurrence. What do I mean by multiplicity? Multiplicity is the multiple number of ways in which a particular macroscopic outcome is possible. There are two ways in which this head-tail outcome, macroscopic outcome, is possible. So a disordered state has got higher multiplicity, and here is something that I've written at the bottom of this page. Hence, this disordered state has a greater probability of occurrence because it has got a higher multiplicity. Entropy is the measure of that disorder. How do you know? See, this macroscopic outcome has got a higher multiplicity. Omega, capital omega is the multiplicity. It was Boltzmann who showed that in any natural phenomenon, if you have a higher multiplicity, sorry, multiplicity is connected to the entropy of that state. Just think of something. You've got a pile of rubble. You apply explosive to that pile of rubble, and all the material is thrown up in air, right? It will again fall back and form another pile of rubble in a slightly different configuration, maybe. What are the chances that it will fall back in such a way that it will the thing the rubble, the material that has all the masonry material, stone and mortar, marble, everything that has fallen back would suddenly assume the configuration of, let us say, the Taj Mahal. Theoretically, it is possible. Practically, it is extremely improbable. The things will get thrown up and then suddenly falling back. Or you break a plate, right? Just think of this one little discussion. You have a plate, bone china plate, you have dropped it from your hand, it has fallen through air to the ground, it has fallen through a certain height. Right, GH is the energy, mgh is the energy that has been acquired as it has fallen, and that part of that energy has gone into the plate as it struck the ground and broken it. Now I say that, hey, you've broken the plate. Now, what will you do to restore it? You will say, well, let me try to see. I have calculated the amount of energy that has gone into breaking the plate. So what I will do is that I'll put all the broken pieces together in a fridge, and in a fridge, energy will be sucked out because the objects will become colder inside a fridge. What do you mean colder? Meaning that its energy is being sucked out, thermal energy is being sucked out. So energy will be sucked out of it. So whatever energy has gone into breaking the plate has been drawn out. Will the plate again become intact? Unfortunately, no. Why not? Because the plate has gone into a higher state of disorder after it has become broken. Meaning, higher state of disorder, here is the formula. Entropy is proportional to log of multiplicity. Higher multiplicity is connected to disorder. Higher disorder, higher multiplicity. Head-tail combination here has got a higher disorder and a higher multiplicity. Hence, this disordered state has greater probability of occurrence. More the value of omega, greater the value of the multiplicity, greater is the entropy. Entropy is the measure of that disorder. Now you see multiplicity or breaking of the plate, all these things. A breaking of the plate is disorder, but multiplicity is a microscopic view. I'll say, what is the multiplicity here? You'll have to count. Coin 1 is head, coin 2 is tail. Coin 1 is tail, coin 2 is head. These are the microscopic ways in which this thing can happen. The head tail combination can happen. So multiplicity is a microscopic measure. But entropy overall is a macroscopic measure. Entropy is a measure of the overall disorder of the system. You don't go inside the plate and see along which track a fault line in the china material has the crack happened. There's no point. The plate has gone into, a higher state of disorder overall anyway. Incidentally, thermodynamics, follow this point carefully, thermodynamics deals with the macro, macro, macroscopic thing. Temperature is a thermodynamic quantity. Pressure is a thermodynamic quantity. Entropy coming out of the second law of thermodynamics is a thermodynamic quantity. But average energy is a microscopic quantity. Multiplicity is a microscopic quantity. So these things are to be found statistically. When I say find the temperature, you don't do any statistical analysis. You don't count particle by particle. When I say find the entropy, you just look at the overall disorder into which a system has gone. Incidentally, that is also the reason why people never come back to life after they die. Why? Because death is a state of higher disorder. Life is a highly ordered state. You imagine, just look at yourself. Slight change of enzymic reaction and you will fall sick. The human body, your body is in an exquisite state of balance set by nature. It is a highly ordered state. A little change here and there, and you'll immediately feel the effect. But when a human being dies, all that order comes to an end. The body goes into this entire form, physical form goes into a highly disordered state, and anything that goes into a greater state of disorder can't reverse that state. That's why we say that entropy is a quantity that always keeps growing in the universe. Nature's own tendency, I will just give me a minute, I will end in this point. Nature's own tendency is to minimize energy and increase entropy. That is the whole idea. So Boltzmann's constant connects microscopic quantities such as average energy, multiplicity, force exerted by particles, all these things, to macroscopic quantities such as temperature. If I want to find out the average energy contained in your room, all I have to do is find the temperature of that room. Right now, this is winter, it is cold. I'll say the particles are moving with a smaller average energy. In the summer, temperatures will go to 45 degrees, it will be hot, right? So Boltzmann constant, the Boltzmann constant is a bridge between the two. I'll just finish on this point. I finished the technical discussion. I finished the discussion on physics theory. I will just mention something. Just please give me a minute. I'll just mention something. Please just bear with me for a minute or two. See, as we go along, there are some errors in the notes, right? I mean, I will just briefly show you something in your lecture folder. Sorry, in your this folder, Google Classroom. I'll talk about that also in a minute. In your Google Classroom, you'll find these correction sheet as well. There have been various errors in the notes. So as you can, I hope, can you just please confirm that you can see these corrections to physics concepts?
Yes, sir.
Yes, sir.
Yes, yes, yes. Thank you. So there are errors, as I have noted in a few pages separately. Instead of disturbing the old notes, I have listed those errors. You'll get all these things very soon. Yesterday, so that's the other point. Yesterday, I spoke to Mr. Pandya, who is the deputy registrar. He said that 16 students are to enter laterally, so they are just going through their details carefully before they are allowed, because of there's a cutoff mark for the CS branch. All the other batches have been finalized except the CS. All the other class list, because of this cutoff business, so they are just going through. So he is hopeful that by the 4th, that by this Friday, the final class list will be ready. And so hopefully sometime next week, by the middle of next week, probably not on Monday, because Saturday, Sunday will be holidays and we will not have the time to prepare the list. So probably Monday's lab, I will again go by the old mode of sending the email to your entire class and not just the CS batch. Hopefully by next Wednesday, you will have your class list ready and we will start operating from Google Classroom. And so anyway, this Friday we have a class. There we will start our mathematical theory, which has been long pending, which should have started because we have already devoted a lab to that. So next Friday's class, we will begin mathematical theory. We have finished the first of the basic physics concepts. Okay, so I shall stop here now. You'll get the notes and everything in due course. So from your side, if you have any question to ask, you may do so. Otherwise, I'll anyway stop the recording. So because the recording size becomes very large.